For section 12.6, we're going to kind of focus in on outliers here, and we've talked about outliers before. Remember that outliers are observed data points that are far from the least squares line. That's how we're going to define it in this unit, since we were just talking about that least squares regression line. They have large errors, which means they're very far away from that line, where the error or the residual is the vertical distance from the regression line to the observed point. So in this chapter, that's how we'll define outliers. Previously, we had that definition of it had to be 1.5 interquartile ranges away from certain things, but we're going to focus in kind of on the, since we're dealing with bivariate data, we're going to focus in on that regression line. Note, as a rough rule of thumb, we can flag any point that is located further than 2 standard deviations above or below the best fit line as an outlier. And you're going to see an example like that in your homework, and they give you the best fit line, then they give you 2 standard deviations each way, and you're supposed to identify as an outlier anything that's outside of those 2 standard deviations away. In order to perform a residual analysis on a regression model, and remember the residual is the error, or it is the distance between the observed value and the predicted value from our line, residuals play an important role in determining the adequacy of the linear model. In fact, residuals can be used for the following purposes. First of all, to determine whether a linear model is appropriate to describe the relation between the predictor and the response variables. Another thing we can use it for is to determine whether the variance of the residuals is a constant. And finally, to check for outliers. If a plot of the residual against the predictor variable shows a discernible pattern, such as a curve, then the response and predictor variable may not be linearly related, even if it seems like they would be. So here's how we can draw a residual plot. First of all, we will enter the raw data in L1 and L2, as we have done previously. Then we will obtain our least squares regression line. That's our linear regression, as we've done previously. Then step 2, access the stat plot and select plot number 1. Choose the scatter plot diagram icon, and let the X list be L1. And everything we've done up to this point, we've done before. Now this is where it's going to get a little bit different. Let the Y list be this label right here, residual. And we're going to find that residual by moving the cursor to Y list and then pressing second, stat, and then choosing number 9. We found out on our calculators it's actually not number 9. I believe it's number 7. So we're going to choose number 7, the residual, under the names menu. On your calculator, it might be number 8. It just kind of depends on the model. Then number 3 is press zoom and select number 9 for zoom stat, and that will show us the residual plot. For example, 12.15, a chemist has a 1,000 gram sample of a radioactive material, and this chemist records the amount of radioactive material remaining in the sample every day for a week and obtains the following data. The data is given here in the table. So let's go to the next slide and we'll pull up the calculator to take a look at this. So we're going to draw the scatter plot with the least squares regression line and then find the linear correlation coefficient and use a residuals plot to determine whether the linear model is appropriate. So let's start out by turning our calculator on and going to stat and edit. And I'm going to clear out some of these values here because we don't need them right now. All right, so we're going to enter in the days just 0 through 7. So 0, 1, 2, 3, 4, 5, 6, 7. And then we'll enter the values for the weight. 1,000, 897.1, 802.5, 719.8, 651.1, 583.4, 521.7, and 468.3. So those are our data points. We're going to draw the scatter plot here. So remember, we're going to go second y equals. Number one, I'm going to turn that plot on. And then I want this option highlighted, which it is. That is our scatter plot. And initially here, I'm just going to leave the X list as L1 and the Y list as L2 because we're going to look at the scatter plot to begin with. So we're going to go zoom and then 9. And looking at that, it looks pretty linear, doesn't it? So let's take a look and let's find our line of best fit. So we're going to go stat and over to calculate and down to number 4. That is our linear regression. That needs to be L1 for the X list. The Y list is L2, and then the frequency, that's fine, and then calculate. So we get this value for our line of regression, y equals, and the A value is negative 75.296. That has an X value with it. In our formula right up here at the top, remember we're plugging in the A and the B into that pattern. Then the B value is 969.025. Okay, so let's go ahead. Oh, and also notice it asks for the linear correlation coefficient, R equals negative 0.9941, which is a really good model. And if we look at R squared, 0.988, remember that what that tells us is that 98.8% of these data points are well represented by this linear regression line. So let's go to y equals, and let's clear that out, and let's type this in, negative 75.296 x plus 969.025. And I don't need that arrow there anymore, so let's get rid of that. And then we're just going to graph it again, and we're going to see. All right, well, look how that line does a really pretty good job of modeling those data points. So that's our scatter plot. That's our least squares regression line. We found the linear correlation coefficient. And now we're going to use a residual plot to determine whether that linear model is actually appropriate, because it looks pretty good. We saw the R value. We saw the R squared value. It looks really good. But let's take a look, and let's go back to second y equals. And if you remember here, we had to change L2 into the residual. And the way we do that is second stat, which takes us to the names. And if you go down to number 7, you can see in this calculator, that's number 7. The residual is going to be our y value. Okay? And then if we do zoom 9, we see this. Okay, and this is definitely not a line. This is a curve. And if you remember back a couple slides ago, it says if you see a curve, a pattern such as a curve, then a linear model might not be the best option. And the idea here is, in this area, our residuals are positive, then they become negative, and then they go back positive, and that's telling us we've actually got a curve going on here. Now in this, so we find out that a linear model is not the most appropriate model. It actually turns out, because this is a radioactive substance and it's radioactive decay, actually an exponential model would be the best model here. Even though when we looked at it, it looked pretty linear, and even though the R squared value was pretty linear, if you extended that out and kept going further and further in your days past 7, you would find out that it's actually an exponential model. So that's how we can use the residual to help us, the residual plot to help us see if a linear model is actually the appropriate or the best model for this particular data. Another note we want to make is that if a plot of the residuals against the explanatory variable shows the spread of the residuals increasing or decreasing as the explanatory variable increases, then a strict requirement of the linear model is violated. What should happen with those residuals is you should, if it's linear, what should happen with those residuals is they should be very close to 0, sometimes above, sometimes below 0, but it shouldn't be a distinct pattern. So if your residuals were increasing, so here's your 0, if your residuals were increasing, well, that's telling you that the line is not modeling it very well as you go further to the right. Or if the residual is decreasing, it tells you that the residual is not modeling very well as you look at the left side of the graph. So, or the line, sorry, is not modeling very well as you go to the left side of the graph. So looking at that, that's the sort of thing we're talking about here, and we need those residuals to stay pretty close to zero. And like I say, some of them might be above, some might be below, but they need to stay pretty close to zero and not have that distinct, like a curve like we saw in that last one. Another thing that we can do with residuals is we can draw a box plot that shows the residuals or graphs the residuals. So what we would do again is enter the raw data in L1 and in L2. Then we would highlight L3 like we've done before when we put in a formula for L3, but this time we would highlight L3, press second, and then list, and then select option number 7, the residual, and press enter. Yeah, my 3 got in the wrong spot there. 3, we would go to the stat plot and highlight the box plot icon, which I'll show you how to do that, and then enter L3 in the X list field. Then press zoom and zoom stat. Let's go ahead and look at this one, and then we're going to make a box plot of this one. It says draw a residual plot on the drilling time data that we've been using previously. Comment on the appropriateness of the linear least squares regression model. Produce a box plot of those residuals. So I've taken the time to type in these values. Notice the L1 is our depth that the drilling begins, and then the L2 is the drilling time in minutes to drill 5 additional feet. What we're going to do now is go over to L3, and we're going to highlight L3, and we're going to push second stat, which is our list menu, and we're going to go down to number 7, the residual. And when we hit enter here, it's going to enter in all those residuals. So that's what we're going to make a box plot on. So we're going to go second y equals. Number 1 is still on, and that's fine. But we're going to go down to type. And the box plot, if you remember, that's going to be this option right here. So we're going to hit enter there. And we're going to go to X list. And once again, we're going to put in L3. So second 3 turns that into L3. And then we're just going to go zoom 9 to give us the best picture. Oh, I don't know what happened there. That happened on somebody else's too. Let's just zoom quit. And then we'll go zoom 9, or second quit, and then zoom 9. And we can see our box plot there. And so it says comment on the appropriateness of the linear squares regression model. Produce the box plot. So here's our box plot. We've already talked about this example a whole bunch of times. And we saw that a linear model was okay, but not super amazing. And what you're going to have here, if your box plot is pretty much even in all of the quartiles, then your residual model should be pretty good, or your linear regression model should be pretty good. Notice this one here is pretty short in comparison to the other ones, and then these two are both kind of long. And if you remember, that's what happened as we went further and further to the right. That data kind of got more spread out, sometimes above and sometimes below the regression line, but that's the scenario there. If that stays pretty even, each quartile about the same size, then we're pretty good. If it ends up being kind of scattered like that, then we'll have evidence to say it's probably not the best fit. A linear model is probably not the best fit for what we've got, or at least it's not a strong fit. Related to these outliers is what we call an influential observation, and this is an observation that significantly affects the least squares regression line slope and or y-intercept, or the value of the correlation coefficient. So again, it's related to outliers because that's typically what those influential observations are going to be. They're going to be something that drastically changes some of our modeling data. So looking at 1217, suppose an additional data point is added to the drilling data at a depth of 300 feet. It took 12.49 minutes to drill 5 feet. Is this point influential? So notice I've got our previous line of regression here, and we're going to go to the calculator and we're going to type in that additional point and then see if that is gives us a change in the slope and the intercept there. So we're on our box plot. We're going to go back to our list. So stat, and we're going to go to edit. And I'm just going to clear off list 3. We're not going to use that anymore. So I'm going to go over here, and we need to add an additional point to list 1, and that additional point has a depth of, whoops, went too far, has a depth of 300, and it has a drill time of 12.49. Now the first thing I want to do is I want to go back and look at a scatter plot just to see what's going to happen visually. So second y equals, I'm going to change this back to a scatter plot. And I'm going to go to list 1. And for the y list, I'm going to go to list 2. Okay, and then I do want to make sure I clear off, I did already clear off that equation. So zoom 9 will take us to that scatter plot. So notice these were the ones that we had seen already in previous lessons. And that is, let me move this back over if I can. So that, oh, that moved that too. Okay, let's fix that up. These are the ones that we had seen previously. And so what we're looking at now is this one up here. Is that going to be an influential point? Well, if we continue these out kind of with the trend that we have, we can see it looks like it's probably an outlier. It is not very much in line with what we've got. But let's take a look at what happens with our line of best fit. So we're going to go stat and over to calculate. Let me erase those green markings. We're going to go down to number 4. And list 1 and list 2 is correct. And we're just going to calculate that line of best fit. And here's what we get. So we're going to compare it to this one. Y equals 0.0212x. And then it's plus 4.443. Okay. The R values, I don't remember what the R value was before. It actually seems like that R value is better now than it was before. But notice here what we're looking at, changing from 0.0116 to 0.02, that is almost doubling the slope. Okay, and so when you see something where the slope almost doubles, even though it's a relatively small number, it's actually almost doubling that slope. That is going to be an influential point. So yes, that is an influential point. And our reasoning is the slope doubles. Okay. Now, one other thing I wanted to show you, because this happens in your homework, if we go back to our list, if we go to stat and go to enter, let me get rid of our white line there. If we need to get rid of an outlier or an influential point, the way we do that, if we need to get rid of any point, so I'm just going to pick one here. I'm going to pick the 95 and the 6.1. But if I need to get rid of that point, all I do to get rid of it is I'm going to push delete. And notice that point is gone. And if we go down to the bottom of our list, we'll notice now that the list 1 is shorter than list 2. So we would also need to go up and delete that 6.1 that I mentioned, which was corresponding to the 95. And we hit delete there, and that will delete that one. And now we've eliminated that point from our data set, and we are back to having the same number of points. So I know that there's one in the homework where it asks you to find the line of best fit for the original data set and then after the outlier is removed. So make sure that you kind of remember how to do that with that delete key. That is the end of section 12.6. There are 4 graded problems there. As you probably have guessed, it's going to have a few different parts to those problems. As you are given a data set, you type it in, and then you have to answer several questions based on that data set. But again, if you have any questions, please make sure you let me know, and I'll try and get back to you as soon as I can on that.